Night settled over South Australia with a kind of quiet that belonged only to vast places, far from the coastal cities. The interior darkened into a featureless expanse where distance erased detail and the land dissolved into shadow. From altitude, there were no street grids, no moving headlights, no reference points to confirm motion or scale. Only scattered farm lights and the faint geometry of isolated roads hinted that the earth below was inhabited at all. High above that darkness, a twin-engine jet moved steadily through smooth air. The aircraft's polished fuselage reflected nothing. The night absorbed it completely. Inside the cockpit, instrument panels cast a subdued amber glow across the faces of the two pilots. Needles held steady. Engine gauges showed symmetry. The aircraft was functioning precisely as designed, translating thrust into forward motion with quiet efficiency. The descent had begun minutes earlier, initiated according to routine timing. There was no urgency in the cockpit. The process followed a familiar cadence: altitude checks, navigation confirmations, radio calls delivered in measured tones. The crew had flown routes like this many times before. The aircraft, a McDonnell Douglas DC-9, was built for exactly this kind of operation. Short to medium sectors linking distant cities across wide terrain. Below them, the land rose gradually, though nothing in the darkness suggested elevation. In daylight, the region revealed low ridges, dry riverbeds, and irregular plateaus shaped by erosion over millennia. At night, those contours flattened into invisibility. Without visual contrast, terrain awareness depended entirely on instruments and procedural discipline. A thin layer of cloud drifted at lower altitude, not dense enough to be called a storm, but sufficient to obscure any remaining ground detail. The aircraft passed through it briefly, a momentary blur against the windscreen, before emerging again into clear air. Moisture streaked backward along the glass, illuminated by the landing lights, then vanished into darkness. Inside the cabin, most passengers remained unaware of the landscape below. Reading lights formed a constellation of small halos along the aisle. Some travelers slept, heads tilted toward windows that reflected only their own silhouettes. Others watched the faint vibration of the wing, a reassuring sign of continuity rather than instability. In the cockpit, attention narrowed. Descent profiles require anticipation rather than reaction. Too shallow, and the aircraft arrives high and fast. Too steep, and energy margins tighten. The crew monitored vertical speed and distance with practiced efficiency. Outside, the horizon was indistinguishable from the ground, a seamless black field interrupted only by the aircraft's own lights. Air traffic control communications were brief, procedural. Radar coverage in remote regions was limited, and separation often relied on position reports rather than continuous surveillance. The crew acknowledged instructions, adjusted headings incrementally, and continued downward. Each step brought the aircraft closer to terrain that remained unseen. The DC-9 systems provided reliable data, but they belonged to an era before comprehensive terrain awareness technology. Altimeters measured height above sea level, not distance from the ground immediately below. Navigation aids indicated position relative to radio beacons that might be dozens of kilometers away. The aircraft could know precisely where it was in abstract terms while remaining blind to the contours rising beneath its flight path. A subtle shift in engine tone marked another power adjustment. The descent stabilized. Airspeed remained within planned limits. Nothing suggested deviation from normal operation. Yet the margin between safe altitude and unseen terrain was narrowing, measured not in miles but in minutes. Far below, the land continued its gradual ascent toward a series of low highlands. In daylight, pilots navigating visually would note the change easily. At night, with no moonlight and minimal ground illumination, the terrain might as well have been an ocean, black, depthless, and without texture. The aircraft pressed forward, guided by instruments, procedure, and expectation. The routine nature of the flight concealed how dependent it had become on accurate interpretation of limited information. There was no alarm, no sudden failure, no dramatic weather. Only the steady continuation of a descent into a region where small miscalculations could carry irreversible consequences. In the final minutes before the accident sequence began, the cockpit remained composed. Checklists were completed. Radio frequencies adjusted. The aircraft crossed invisible thresholds in the sky, altitudes where decisions would soon matter more than routine. Nothing in the pilot's immediate perception indicated danger. The instruments did not warn of terrain ahead. The darkness outside offered no contradiction. The aircraft continued downward into the silent interior of the continent, toward ground that neither crew nor passengers could see. In the late 1970s, commercial aviation stood at a transitional point between the pioneering decades of jet travel and the technology-driven safety culture that would follow. Aircraft had become faster, more reliable, and economically essential to national infrastructure, yet many of the systems now considered fundamental to flight safety were still evolving. Terrain awareness technology was limited. Ground proximity warning systems existed, but were not universally mandated. Radar coverage outside major metropolitan areas remained incomplete. Much of aviation safety still depended on procedural discipline and human interpretation of imperfect information. Australia's geography amplified these limitations. The continent's population clustered along the coast, leaving vast interior regions sparsely inhabited and minimally equipped with aviation infrastructure. Flights between cities often crossed hundreds of kilometers of terrain with few visual references and limited navigation support. At night, these routes became corridors of isolation, where aircraft moved through controlled airspace that could quickly give way to procedural control based on position reports rather than continuous monitoring. South Australia embodied this contrast between modern aviation and remote landscape. Its capital, Adelaide, functioned as a gateway between coastal urban life and the interior's wide expanses of arid land. Routes linking Adelaide to smaller regional centers required crews to operate confidently beyond the reassurance of dense ground infrastructure. Pilots flying these sectors developed a professional familiarity with remoteness, an acceptance that precision depended less on external guidance and more on adherence to procedures refined through experience. By 1977, the McDonnell Douglas DC-9 had established itself as a workhorse of short and medium-haul aviation. Designed in the early 1960s, it prioritized efficiency on routes connecting cities separated by moderate distances. Its twin rear-mounted engines allowed operations from shorter runways, making it particularly suitable for regional networks. Airlines around the world relied on the DC-9 to sustain domestic connectivity, including in countries where geography imposed operational challenges. The aircraft reliability fostered confidence. Crews regarded it as predictable, responsive, and robust under normal conditions. However, like all aircraft of its era, it depended on navigation technologies that required constant human oversight. In modern cockpits, digital terrain mapping and satellite positioning provide a continuous picture of an aircraft's relationship to the ground. In 1977, navigation relied on radio beacons, inertial estimates, and charts that translated geography into procedural constraints. The aviation industry was also confronting a growing recognition of controlled flight into terrain accidents worldwide. These incidents shared a troubling pattern. Fully functional aircraft, flown by competent crews, descending into terrain without awareness of the danger until it was too late. Investigators increasingly identified situational awareness, rather than mechanical failure, as a decisive factor. The absence of automated terrain warnings meant that crews bore sole responsibility for maintaining safe altitude relative to unseen ground. Air traffic control systems reflected similar constraints. Radar coverage was strongest near major airports but diminished with distance. Controllers relied on pilots' position reports to track aircraft across remote sectors. Communication clarity and timing became critical. Misunderstandings or delayed updates could leave crews operating with incomplete information about their environment. In such conditions, Procedural altitude restrictions served as invisible safeguards, defining the minimum heights required to ensure terrain clearance. Weather patterns in South Australia added another layer of complexity. While the region did not experience the intense storm systems common in tropical climates, it frequently produced low cloud layers, reduced visibility, and haze that obscured terrain features. Night operations compounded these effects. Without moonlight, even significant landforms disappeared into uniform darkness. Pilots transitioning from instrument reliance to visual approach cues sometimes encountered a disorienting absence of reference points. The airport involved in the 1977 accident functioned as a critical link for regional travel, yet its facilities reflected the era's limitations. Navigation aids were reliable but not comprehensive. Approach procedures assumed disciplined adherence to published altitudes and distances. Unlike major international hubs, regional airports often lack sophisticated monitoring equipment capable of detecting deviations in real time. Responsibility for maintaining safe descent profiles rested primarily with the flight crew. Passenger aviation during this period also carried a cultural expectation of routine reliability. Flying had become commonplace, stripped of the novelty that characterized earlier decades. Travelers boarded domestic flights with confidence shaped by years of safe operations. For many, these routes represented ordinary transitions between work, family, and obligation, journeys measured in hours rather than experiences of risk. The flight in question departed within this context, a routine service across a familiar route, operated by a proven aircraft type, crewed by professionals trained to manage the demands of regional aviation. Nothing in the schedule suggested unusual difficulty. No extraordinary weather systems threatened the path. Maintenance records indicated an aircraft functioning within expected parameters. Yet aviation accidents rarely arise from singular causes. They emerge from chains of conditions that align gradually, often invisibly. A procedural assumption here, a limitation there, an environmental factor that narrows margins without announcing itself. Each element appears manageable in isolation. Together, they can create a pathway toward catastrophe that remains indistinguishable from normal operation until the final moments. As the DC-9 continued its descent toward South Australia's interior, it carried with it the strengths and vulnerabilities of its time. Dependable machinery, skilled personnel, and a system still learning how to protect against hazards that could not be seen. Understanding how a modern airliner could be guided into unseen terrain requires examining the separate elements that govern the flight: the machine, the people operating it, the environment through which it moved, and the procedural systems intended to keep all three aligned. Accidents of this type rarely originate in a single failure. They develop where layers of protection thin simultaneously, leaving routine operations exposed to risks that no individual participant fully perceives. The aircraft, McDonnell Douglas DC-9. The McDonnell Douglas DC-9 represented a generation of jetliners engineered for efficiency rather than technological redundancy. Introduced during a period when airlines demanded reliable short-haul capability, the aircraft emphasized structural strength, responsive handling, and operational flexibility. Its twin rear-mounted engines reduced noise in the cabin and allowed operation from runways that could not accommodate larger jets. For regional carriers and domestic routes, it became indispensable. In the cockpit, the DC-9's instrumentation reflected the analog era of aviation. Flight information was presented through mechanical gauges, altimeters with rotating needles, vertical speed indicators responding to pressure changes, attitude indicators stabilized by gyroscopes. Each instrument conveyed a single parameter. Situational awareness emerged only when pilots synthesized these readings into a coherent mental picture of the aircraft position in space. Navigation systems relied heavily on ground-based radio beacons. Very high-frequency omnidirectional range (VOR) stations provided directional guidance, while distance-measuring equipment (DME) indicated how far the aircraft was from a specific transmitter. By cross-referencing multiple signals, crews could determine position with reasonable accuracy. However, These systems described lateral location more reliably than vertical safety. Knowing distance from a beacon did not reveal whether terrain between the aircraft and destination rose unexpectedly. The DC-9 was equipped with an early ground proximity warning system in some configurations, but adoption was not universal and performance varied. Early GPWS units depended on radio altimeter data and descent rate calculations. They were effective in certain scenarios but could fail to provide timely warnings if terrain rose gradually rather than abruptly. The system's logic assumed specific patterns of danger, leaving gaps where controlled descent toward elevated ground might not trigger alerts until recovery was impossible. Autopilot capabilities were similarly limited compared to later generations. While the system could maintain altitude, heading, and descent rates, it required careful monitoring. Automation reduced workload but did not eliminate the need for constant verification. In complex environments, reliance on autopilot could introduce subtle complacency, a belief that stability equated to safety. Structurally and mechanically, the aircraft was not predisposed to failure. Engines performed within expected parameters. Control surfaces responded normally. There was no inherent defect guiding it toward danger. The DC-9 was functioning precisely as designed, executing commands without question. The crew, the pilots, represented the human interface between machine and environment. Training programs of the era emphasized procedural compliance, aircraft handling skills, and navigation proficiency using available instruments. Simulator technology existed but lacked the realism of later decades, limiting exposure to rare or ambiguous scenarios, such as night descents over featureless terrain. Cockpit culture in the 1970s tended toward hierarchical structure. Captains held primary authority, with first officers expected to support decisions rather than challenge them unless a clear safety issue emerged. This dynamic promoted efficiency but could suppress uncertainty when conditions became ambiguous. Situational awareness depended not only on individual competence but also on communication clarity within the cockpit. Fatigue management standards were less developed than modern regulations. Duty schedules sometimes required crews to operate during circadian low points, when alertness declined naturally. Even mild fatigue could affect perception, increasing susceptibility to visual illusions and reducing capacity to question assumptions. Importantly, the crew was not inexperienced. They were professionals accustomed to regional operations, familiar with the aircraft, and trained to manage routine descents into airports with limited infrastructure. Their competence was not in doubt. What mattered was how human cognition interacts with environments that provide incomplete feedback. The environment. South Australia's interior presented a deceptively gentle landscape. Unlike mountainous regions where terrain hazards are obvious, the area consisted of low elevations that rose gradually over long distances. This topography could mask danger. Pilots descending according to expectations might not perceive that the ground beneath them was steadily climbing to meet the aircraft's path. Night conditions intensified this ambiguity. Without artificial lighting, the horizon vanished. The absence of visual reference points eliminated depth perception. A phenomenon known as black hole approach could occur when aircraft descended over unlit terrain toward a sparsely illuminated airport. Pilots might unconsciously lower the glide path, interpreting darkness as distance rather than absence of detail. Weather added further complexity. Thin cloud layers and haze scattered light from the aircraft itself, reflecting back toward the cockpit and reducing forward visibility. Even in clear air, humidity could create subtle visual distortions, blurring the boundary between sky and ground. None of these conditions constituted severe weather, yet collectively they eroded the cues pilots relied upon to confirm altitude visually. The terrain itself offered no warning. There were no sharp peaks silhouetted against moonlight, no urban glow revealing elevation changes. The aircraft approached a region where the ground rose silently, hidden beneath darkness that instruments alone had to interpret correctly. Systems and procedures. Air traffic control provided guidance but operated within technological limits. Controllers could assign altitudes and headings, yet continuous radar tracking was not guaranteed across remote sectors. Once an aircraft left primary coverage, monitoring depended on pilot reports and estimated positions. Controllers trusted crews to maintain safe altitudes unless deviations were reported. Published approach procedures defined minimum altitudes designed to ensure terrain clearance. These altitudes assumed accurate navigation and timing. Descending prematurely or misjudging distance from reference points could place an aircraft below safe limits without immediate indication of danger. Chart available to crews displayed terrain contours and procedural constraints, but interpreting them in real time required attention and anticipation. Workload increased during descent, as pilots managed communication, navigation adjustments, and configuration changes simultaneously. In such phases, the margin for unnoticed error narrowed. The system as a whole functioned on the premise that each component, aircraft instrumentation, crew judgment, environmental awareness, and procedural adherence, would compensate for the other's limitations. When all operated correctly, the result was safe and efficient flight. When small discrepancies aligned, the safeguards weakened. On that night in 1977, none of these elements failed dramatically. Instead, they interacted in ways that reduced the crew's ability to perceive the developing hazard. The aircraft continued to descend, guided by procedures that assumed accuracy and awareness. The environment provided no visual contradiction. The instruments presented data requiring interpretation, rather than issuing unequivocal warnings. The convergence of machine capability, human cognition, environmental ambiguity, and systemic limitations formed the silent framework within which the accident would unfold. By the time the aircraft crossed the invisible boundary between cruise descent and approach preparation, the margin for correction had already begun to narrow. The transition was procedural, almost routine. A checklist completed, a frequency changed, a descent clearance acknowledged. Nothing in the sequence suggested that the flight had entered a phase where precision mattered more than habit. The DC-9 continued downward through smooth air, its engines producing a steady, subdued thrust. Vertical speed remained within expected limits. From the cockpit perspective, the descent profile appeared orderly, consistent with countless previous arrivals. Instrument needles moved predictably. No alarm sounded. No abnormal vibrations disturbed the A-frame. Distance to the destination was calculated using radio navigation references that existed as invisible points in space. The aircraft position relative to those points determined when descent milestones should occur. A misinterpretation, even a small one, could shift the entire profile forward or backward without immediate detection. In darkness, there was no visual cross-check to confirm whether the aircraft was truly where the instrument suggested. Below, terrain rose gradually toward a plateau that extended across the aircraft's path. The change in elevation was so subtle that even daylight might not have revealed it from high altitude. At night, it remained indistinguishable from the surrounding landscape. The aircraft descended toward ground that was approaching faster than expected, though nothing in the cockpit yet conveyed that reality with urgency. Communication with air traffic control remained calm and procedural. Altitude reports were acknowledged. Clearances confirmed. Without radar visualization of the aircraft's precise height above terrain, controllers relied on the assumption that published minimum altitudes were being observed. The system depended on shared understanding rather than direct oversight. Inside the cockpit, workload increased as the crew prepared for approach configuration. Navigation radios were adjusted, approach charts referenced, descent rates refined. Each action demanded attention, fragmenting situational awareness into individual tasks. The human brain, efficient at managing routine sequences, can struggle to maintain a broader picture when multiple details compete for focus. At a critical moment, the aircraft descended below the altitude that ensured terrain clearance for that segment of the route. The deviation was not dramatic, only a gradual continuation of descent where level flight should have been maintained. Without terrain visibility or automated warning, the error remained concealed within otherwise normal instrument readings. The ground proximity warning system, if installed, did not provide a decisive alert in time. Early systems were designed primarily to detect steep descent toward terrain directly below, not the controlled approach of rising land ahead. The aircraft descent rate appeared acceptable, masking the closing vertical distance between fuselage and earth. Seconds accumulated. Airspeed held steady. The altimeter unwound with mechanical indifference, marking the aircraft's height above sea level, not the plateau now directly ahead. In the darkness beyond the windshield, the horizon remained invisible, denying the crew the visual cue that the aircraft flight path intersected with terrain. The first unmistakable indication came too late to alter the outcome. As the aircraft neared the ground, peripheral awareness shifted, a subtle recognition that something was not aligned with expectation. Whether through a fleeting visual impression, instrument cross-check, or instinctive unease, the realization emerged in the final moments that the descent had continued beyond safety margins. Control inputs were applied in an attempt to arrest the descent. Engines responded, spooling toward higher thrust. The aircraft's nose began to rise. But jet engines require time to produce full power, and momentum carries an aircraft forward even as climb is initiated. The available distance between aircraft and terrain had already been consumed. The DC-9 struck the rising ground at high speed while still under control flight. There was no evidence of structural failure preceding impact, no loss of control in the aerodynamic sense. The aircraft remained intact in the air, responding to commands until the instant terrain intervened. The collision occurred in darkness, far from populated areas. Sound dissipated across the empty landscape without witnesses nearby to interpret it. Debris spread along the impact path, marking the abrupt end of a flight that, moments earlier, had appeared entirely routine. In aviation terminology, the event would later be classified as controlled flight into terrain, a phrase that conveys the chilling paradox of a functioning aircraft guided unintentionally into the ground. It reflects not chaos, but the absence of awareness until recovery is impossible. Silence returned quickly to the plateau. Above it, the night sky remained unchanged, indifferent to the loss below. The route that had guided the aircraft across the continent now passed over a site that will become a point of investigation, memory, and eventual safety reform. The aircraft's disappearance did not immediately reveal its location. In remote regions of South Australia, the absence of radar tracking and the vastness of the terrain complicated the first hours of response. When scheduled communications failed to occur and the aircraft did not arrive at its destination, uncertainty replaced routine expectation. Controllers attempted repeated contact on assigned frequencies, receiving only silence in return. Search and rescue procedures began cautiously, guided by the aircraft's last known position and estimated flight path. Initial calculations produce an area of uncertainty spanning hundreds of square kilometers. In daylight, aerial search crews scan the landscape for signs of wreckage, scorched earth, scattered debris, or smoke. The terrain's muted colors and irregular textures made detection difficult, even from low altitude. The crash site was eventually located in a sparsely populated area where access by ground vehicles proved slow and complex. Investigators arriving at the scene encountered evidence of a high-speed impact consistent with controlled flight into terrain. The distribution of wreckage indicated that the aircraft had been intact and under command at the moment of collision, rather than breaking apart in the air. Recovery teams worked methodically, documenting the position of debris and identifying structural components necessary for analysis. In accidents of this nature, understanding the sequence of events depends on reconstructing both the aircraft configuration and the environment at the time of impact. Each fragment contributed to a broader picture of how a routine descent had transformed into catastrophe. Flight recorders, if recoverable, became central to the investigation. Cockpit voice recordings offered insight into crew actions and communication patterns during the final minutes, while flight data traces revealed altitude, speed, and control inputs. In the 1970s, recorder technology provided less detailed information than modern systems, yet even limited data could confirm whether mechanical anomalies preceded the accident. Investigators determined that the aircraft systems had been functioning normally. Engines showed evidence of producing power at impact. Control surfaces bore signatures of commanded movement rather than uncontrolled deflection. No indication emerged of structural failure, sabotage, or sudden incapacitation. The aircraft had responded to its pilots until the final moment. Attention turned to the descent profile. Analysis of altitude data suggested that the aircraft had descended below the minimum safe altitude required for terrain clearance along that segment of the route. The deviation appeared gradual rather than abrupt, consistent with controlled but misjudged approach. Without terrain awareness technology or visual references, the crew had no reliable indication that the ground was rising ahead. Charts and procedures were examined to determine whether ambiguity or misinterpretation could have contributed. Investigators assessed whether navigation aids provided sufficient guidance and whether the published approach profile accounted adequately for the terrain. The possibility of positional uncertainty, believing the aircraft to be farther from high ground than it actually was, became a central consideration. Human factors specialists evaluated workload and cognitive demands during the descent phase. Preparing for approach requires managing multiple tasks simultaneously, configuring the aircraft, communicating with air traffic control, monitoring instruments, and confirming navigation data. In environments lacking visual cues, reliance on procedural timing can overshadow real-time verification of altitude relative to terrain. The investigation concluded that the accident resulted from a breakdown in situational awareness rather than a single catastrophic failure. The crew had been operating within a system that depended heavily on manual interpretation of data. When that interpretation diverged from reality, no automatic safeguard intervened with sufficient clarity or timing. Regulatory authorities examined the broader implications. Controlled flight into terrain accidents had already prompted concern internationally, and this event reinforced the need for more reliable warning systems. Discussions intensified regarding mandatory installation of improved ground proximity technology capable of detecting terrain ahead, not only directly below. Air traffic control procedures also came under review. The limitations of radar coverage in remote areas highlighted the vulnerability of aircraft operating beyond continuous monitoring. Proposals emerged for enhanced communication protocols and revised minimum altitude requirements to compensate for environmental uncertainties. For the families of those on board, the investigation's findings offered explanation but not relief. Aviation safety improvements often arise from tragedy, transforming individual loss into collective protection. Memorials and official acknowledgments recognize the human cost while emphasizing the commitment to preventing recurrence. Within the aviation community, the accident became part of a growing body of evidence demonstrating that technological advancement was essential to complement human skill. Pilots could manage complex machines with precision, yet they remained vulnerable to conditions that concealed critical information. Safety would increasingly depend on systems designed to reveal what human perception could not. The crash site, once a point of violent disruption, gradually returned to stillness. Investigative teams departed. Documentation replaced physical presence. The landscape absorbed the traces of activity, leaving only subtle reminders that an event of consequence had occurred there. In aviation, The true measure of an accident is not only the loss it causes, but the changes it compels. The 1977 South Australian DC-9 crash entered the historical record as another instance of controlled flight into terrain, a category of accident that forced the industry to confront the limits of human perception in environments stripped of visual reference. The aircraft had not failed. The crew had not acted recklessly. Instead, the system surrounding them had allowed a gradual erosion of situational awareness to pass undetected until recovery was no longer possible. Investigators and regulators recognized that procedural discipline alone could not compensate for invisible hazards. Pilots navigating at night over unlit terrain required tools capable of translating geography into immediate, unmistakable warnings. The concept was straightforward. If human senses could not perceive rising ground, the aircraft itself must assume that responsibility. In the years following the accident, ground proximity warning technology advanced rapidly. Enhanced systems incorporated terrain closure rates, configuration awareness, and predictive logic designed to alert crews before safe margins were compromised. Audible warnings, clear, direct, impossible to ignore, replaced ambiguous cues. What had once been optional equipment became increasingly recognized as essential. Training philosophies evolved as well. Aviation authorities began emphasizing crew resource management, encouraging open communication and cross-checking within the cockpit regardless of rank. Situational awareness was reframed as a shared responsibility rather than an individual burden. Scenarios involving night operations over featureless terrain became standard components of simulator programs, exposing crews to conditions that earlier generations encountered only in real flight. Approach procedures were reviewed to ensure greater safety buffers. Minimum altitudes were reassessed with consideration for navigational uncertainty and human error. Charts became more explicit, highlighting terrain hazards and emphasizing the consequences of premature descent. Air traffic control agencies expanded radar coverage where feasible and refined protocols for monitoring aircraft operating beyond direct surveillance. The accident also contributed to a broader cultural shift within aviation. Safety was no longer defined solely by mechanical reliability. It became a multidimensional discipline integrating technology, human factors, and systemic resilience. Each layer reinforced the others, reducing the likelihood that a single misinterpretation could lead to catastrophe. For the families affected, these changes carried a quiet significance. Improvements in procedures and equipment could not alter the past, but they ensured that the lessons derived from loss would protect future travelers. Every modern aircraft equipped with terrain awareness systems carries, in part, the legacy of accidents that reveal their necessity. Today, aircraft crossing remote regions of Australia benefit from satellite navigation, digital terrain databases, and continuous communication capabilities unimaginable in 1977. Cockpits display real-time maps showing mountains, plateaus, and obstacles with precise clarity. Automated alerts activate long before terrain proximity becomes critical. What was once hidden is now visible. Yet aviation's memory remains long. Accident reports are preserved not as relics of failure, but as instruments of prevention. They remind pilots, engineers, and regulators that safety is not a fixed achievement, but a continuous process shaped by experience. Each generation inherits both the advancements and the responsibility to question whether unseen vulnerabilities remain. At the site where the DC-9 struck the rising ground, the landscape endures unchanged. Wind moves across the plateau as it did before the accident, indifferent to the passage of aircraft overhead. Flights continue to traverse the same airspace, guided by technologies designed to ensure that descent profiles align with the terrain below. The story of the 1977 crash concludes not with a moment of impact, but with a quiet determination that followed, the collective effort to understand, to improve, and to prevent recurrence. In that sense, the legacy is not defined by tragedy alone, but by the safer skies that emerge from its lessons. The night over South Australia remains vast and unlit. Aircraft still descend through darkness toward distant runways. But now, laid beneath routine operations, there exists a network of safeguards shaped by history. A silent assurance that the ground below will no longer rise unseen.